This is Module 10, Lesson 3. We're on our last lesson of the module. What we're going to be doing this time is using the circuits in order to do calculations. So we're going to take Ohm's law, which we learned from before, which was V is equal to IR, and we're going to apply it to circuits. Now we've already seen that we can connect circuits as series or parallel circuits. And so which kind of circuit it is will determine exactly how we're going to calculate the voltage, the current, and the resistance. So now this is on your reference table. It is on page 3. You have two little areas. One says series and one says parallel circuits. So in series, how we're going to calculate the current is as follows. It says in series there's only one path, so the current must be the same everywhere. That means at whatever point you are in a series circuit, the current is exactly the same. So I'm going to draw a little one right here for us to follow through with. I'll put some different stuff in it. So as you could tell, this circuit has a light bulb and a resistor. So the current at the battery, at the light bulb, and at the resistor has to be the same all the way through this. We could even put an ammeter in right there. This ammeter is going to read the same current all the way through this. Okay, since there's only one path, the potential difference has to add up to equal the potential difference of the battery. So if this has a potential difference of 1 volt, 2 volts, and let's say it's 3 volts over here at the ammeter, then the total voltage has to be 1 plus 2 plus 3, which is 6 volts. Now the resistance in a series circuit is also the sum of all of the resistances. This is why in your house, if you start plugging up too many things on the same circuit, you can overload the circuit and it'll trip your circuit breaker in the basement or your laundry room or wherever you've got your fuse box, your circuit breaker box. It'll trip the circuit breaker because you've overloaded it. You put too many things on it, because if you add one thing with a resistance of 5 ohms and another with 10 and another with 15 and so on and so forth, those all add up. Right now we're up to 30 ohms and your circuits can only handle so much. So in series, those all get added together, and that makes what's called the equivalent resistance or the total resistance. It says EQ for equivalent, which is just a fancy way of saying total. Now, let's apply this to an example of a circuit. So for the circuit shown, it's asking us to find the values of I1, I2, and I3. So how would we figure out the current at each of these places? This is the type of thing that you're going to be doing for your practice for this. Well, first of all, we have to use what we know about series circuits, which is this. I know that if the current, whatever I find, if I can find the current at any one place, it's going to be the same throughout. So you can break it down and look at individual pieces. I can take this particular part of the circuit right here and go, well, can I find the I for this one right here? I've got this little piece, and I've got this little piece. Well, here's the deal with the particular little circuit. I need to know the voltage at each of these places. You can think of this like 3 little problems. V is equal to IR, V is equal to IR, and V is equal to IR. You can work a little Ohm's law problem for each of these little portions of the circuit. Then you can also work one more V is equal to IR with all of your totals. Like the total voltage is equal to the total current times the total or equivalent resistance. The problem with doing these little bitty ones right now is that I don't know the voltage at each of the places. Because look at what we just said about series circuits. The voltage is not the same throughout. It's added up. Hopefully you see what I'm saying. I know the total voltage, but I don't know the voltage at each spot. So what we're going to have to work with to start with is the total stuff. We know that the total voltage is 12. And I see all of these resistances. If I have the individual resistances for a series circuit, it said that the equivalent resistance is all of those added together. So R1 plus R2 plus R3. Well, that's 3 plus 4 plus 2. So the equivalent resistance of this circuit is 9. If I plug that in here, oops, not that, let's see. Well, come on, not 9 volts, but 9 ohms. Then we can solve for this, and we can see that what we get for our, I'm going to see where I put this from before. Yeah, that's 2.0. What we're going to get for this is going to be 12 divided by 9, which gives us 1.33, like repeating, amps for the whole circuit. I'm just going to keep that in my calculator. It's not asking me for the total current, it just wants the individual, it wants the individual pieces. But here's the deal, my friends. What do we know? I know that in a series circuit, the current is the same everywhere. So if it is 1.33 here at the battery, then it's also 1.33 here, it's 1.33 here, it's 1.33 there. They are going to be the same at every single individual place along this battery. So we just need to sig fig it. I'm looking. This has 2. These all have 2. So we're going to have it down to 2 sig figs. 1.3 amps is going to be all of those. That's I1, I2, and it's I3. They're all 1.33 amps. Now, I didn't ask this question, but what if I wanted to? What if I ask you to find the voltage at each of these places? What would you do? Well, how you're going to find the voltage at each of these places is you're actually going to have to work like little individual problems. So voltage 1, if I ask you to find V1, I would be referring right here where everything else is labeled with a 1, I1 and R1. How I would do that is I would plug in the 1.3 repeating times 3. And since I've got the 1.3 repeating in my calculator, that times 3 is equal to 4. So it's 4 volts. That is V1. What about V2? Well, V2 is another IR problem. What do I know about it? We know the current is 1.3 repeating times 4. So 1.3 whatever times 4, we get 5.3. So it's 5.3 volts right here at V2. V3, we would do the same thing, IR. Well, I is still the 1.3 repeating times 2. So of course that's going to give us 2.7 volts, right? Rounded it to 2 sig figs. Now, if we add all of those up to find the total resistance, it should add up to 12. So we've got 4 plus 5.3 plus 2.7. What do we get? 12. So that's, I'm just showing you some additional questions that I could ask. Now, what if it's parallel? We just have different formulas for parallel. In a parallel circuit, you know that the charge can take different paths, so the current is not equal to each other like it was in a series circuit. It's all added up together. The current through path 1 plus the current through 2 plus the current through 3, etc. The potential difference, your voltage, is in this case the same throughout. It will be the same at each path in your circuit. And then as far as adding resistors in parallel, when you add resistors in parallel, you actually decrease your total resistance. Therefore, the formula for that looks a little weird. It's 1 over the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. I'll make sure that I solve one of these for us to show you how you would answer that. So here's an example. it wants the value of R2 in the circuit shown. Well, we sort of have some work cut out for us in terms of doing this, just because, we've got to think about some things. These are like little thinking games. What do I know about resistance here? I know that the total resistance is them added together, and I'm wanting to find R2. Oops, wrong way. So if I'm wanting to find R2, the problem is I don't know this right here. I don't know the equivalent resistance. I know R1 is 40. We're hunting R2. And I know that R3 is 60. So in order to solve for R2 right here, I'm going to have to know this one. Well, can I find the resistance of the total of the whole thing? Not without a little bit of work. So here's what I do know. I do know the voltage total. The total voltage is 24. And I do know the total I is 1.8. Now, how do I know those particular things? So I know that these are my totals because right here, we know that the battery power, if it's 24 volts and that's all it's got, and we know for a parallel circuit that the total voltage is going to be the same everywhere. So I know that this is my total. And what about this 1.80 amps? Well, the bottom line is this. The amount of charge, it says the current flowing past each point must add up to the total. So here's how I'm thinking about it here, if I get to the right one. The amount of current that comes out of the battery, let's see if I can highlight, through this one little branch right here, through this piece and this, has to be the same because it hasn't had a chance to branch off yet. Now, beyond that point, some of it is going to come down this way in green. A portion of that current, and we'll make this one blue. Some of it's going to go this way in the blue color. And then another little portion of it in orange is going to come this way. Now, by the time it gets back up around here, the orange is going to have to add back up with the blue. So however much current is right here is going to have to be the same amount of current that's right here. Because, think of it like the flow of water. However much water is traveling in this little section part of it's going to branch off and come this way, and part of it's going to go the orange route. By the time it gets back around to this point right here, they've got to add back up together. Then, this little piece right here has to be the same as what it was before. Like the little green piece, it has to be equal to actually what's over here. I could make it yellow instead, although apparently, oh, there we go. It's going to have to add back up to that because I've gained the orange and I've gained the blue, and it's got to be the same thing that I had back here at the beginning. So you're going to have to use a little bit of logic to go with it. So if it's 1.8 right here at this point before it's split, then that is going to be my total current. So I can find my equivalent resistance if we put it into V is equal to IR. We'll have 24 is equal to 1.8 times R. And my R is going to equal 13.3 repeating. Now, this doesn't answer my question, so I don't really care about rounding. I want to keep all of the digits in my calculator and move on with it. But I'm going to take this number right here, and I'm going to stick it right there for 13.33. Now, how we do this from here becomes a fun little math thing. I'm using the word fun somewhat sarcastically. I guess I'm going to have enough room. We'll find out. So what we're going to have is 1 over 13.3 repeating is equal to 1 over 40 plus 1 over R2 plus 1 over 60. Now, we're going to solve for 1 over R2 is what I would do. We're going to subtract the other ones from this side. Minus 1 over 40 minus 1 over 60 equals 1 over R2. Now, what I would do, if it was me, is I would just put this into my calculator, and solve for R. Okay, but first we're going to get 1 over R. First thing I would do is I would solve for 1 over R. 1 over R is going to be 0.033 repeating because we put this into our calculator and let our calculator deal with the funny numbers. Now, if it's 1 over R is this, you are going to have to do the reciprocal because we need to get this to R. I need it not to be 1 over that, but I need it to be the inverse of it. Well, the inverse of that is going to be 30. So what you'll have to do is you can do 1 divided by this and just use your calculator to do 1 divided by the answer. Or there should be an inverse function if you're using a scientific calculator. If I need to help you with this part of it, let me know. We're going to end up with an R of 30 ohms. You can only have the 1 sig fig. I think it actually comes out to be 33. But you can only have 1 sig fig because these only have 1 sig fig. So we're going to get down to 30 ohms. So this is a much more complicated circuit. The reason that it's more complicated is because we have a combination of things. We have what is a parallel circuit right here. I'll highlight it so that we make sure that we're looking at the correct thing. So we have a parallel circuit going on right here in yellow. And then this parallel circuit is wired in series with this resistor over here. So what we're going to have to do in order to solve this particular type of circuit is we're going to have to simplify the parallel part. So what I'm telling you to do is start with the parallel piece, and we want to pretend like this is in series. I want to get it down until it is as if we have one resistor here in red instead of both of these. So how I'm going to do that is I'm going to find the total resistance of this little yellow part of the circuit. Well, since it's wired in parallel, the equation for that is going to be 1 over the equivalent resistance is equal to 1 over R2 plus 1 over R3. Then what we're going to do is we are going to take our resistances. That's going to be 1 over 12 plus 1 over 24. In order to add those together, we'll have to have a common denominator. So that'll be 2 over 24 plus 1 over 24 is 3 over 24. Reduce those down. They're both divisible by 3. So we have 1 over 8. So that means that our equivalent resistance is going to be 8 ohms. So now that we know that this is 8 ohms, what I'm basically doing in my mind is I'm just kind of ignoring that those are there, and I'm pretending now that I have a series circuit. I'm going to highlight my series circuit in, let's use this lovely teal color. So now I'm looking just at this teal colored circuit, it's kind of blue, and we are just focusing on the blue part of this. Well, now that I'm focusing on the blue part of it, I can pretty easily answer my original question, which is what is the potential difference supplied by the power source? Remember, potential difference is voltage, so that's what we're hunting, is we're hunting the voltage. In order to find the voltage of this circuit, I'm going to have to figure out the voltage of the different pieces in the circuit, and I'm going to have to I can do one of two things. I can either figure out the voltage that is going through the individual pieces and add it up, because in series, remember, your equation for voltage is that it's voltage 1 plus voltage 2 plus voltage 3 plus voltage 4, etc. Or the other option is that I can put it into V is equal to R like we've been doing and use our totals for the whole thing. I personally believe that the easiest way would just be to go for this. It would just be to plug it into V is equal to IR. Our total current for this is 2. And how do I know that the 2 amps serves the whole thing? Because my reference table tells me that current in a series circuit is the same at every single point. So if it's 2 amps here, then it's 2 amps at the battery, and it's 2 amps at this resistor, and 2 amps at this resistor. It's 2 amps everywhere. Now my total resistance, or the equivalent resistance in a series circuit, is all of the resistances added together. Your REQ is going to be R of this red thing plus R1. So what is that? That is 8 plus 8. That is 16 ohms. So 16 ohms is going to go right there. What's 2 times 16? It's 32. So our answer is going to be 32 volts. Now, if you chose to do it another way, I'll show you that you can do it a totally different way and still get the same answer. If you didn't want to do it for the totals, you could do it where you worked out that V total is V1 plus V2 plus whatever. We'll use this as one of them and this is the other one. But what I'm going to have to do in order to do it this way is I'm going to have to work two little V is equal to IR problems, one for this resistor and one for this resistor. So if I do V is equal to IR for this one, I'm going to get 2 amps, because we said it's 2 everywhere, times my 8 ohms. What is that? It's 16. Then I'm going to do another little V is equal to IR problem here. We have the same 2 amps, and we have another 8 ohm resistor. So again, that is 16. When I go to plug it in over here, that'll be 16 plus 16, which is still 32 volts. So you have a choice as to how you come up with this, but you should still come up with the same answer. All right, let's do one more of the complex circuits. Same idea. Remember, my first step to you is find the parallel circuit that's inside the larger circuit and simplify it down to 1. So I want to pretend like this is 1 resistor instead of 2. Now this one asks a lot more questions, so I'm just going to be doing a lot more problems with this. But the first step either way is going to be to simplify this down to 1. So how are we going to go about that? Well, I need to do what I did last time. I need to find the equivalent resistance of this. It'll be 1 over 30 plus 1 over 20. Well, how am I going to go about that? You're going to have a common multiple on the bottom. 60 is the common multiple of 20 and 30. That's the least common one. So that'll be 2 over 60 plus, 3 over 60. That gives me 5 over 60, because remember when you add fractions, you add the tops if they have the same denominator. Well, then this can be reduced to 1 over 12. That means my REQ is 12 ohms. That's a really bad ohm right there, but that's okay. So, we now know that this is an equivalent resistance of 12 ohms. So I'm kind of ignoring these two pieces as far as working part of the larger problem, okay? So now, if I know that that is 12 ohms, I can start to look at what it wants to know. I may still need these pieces of information, or I may not. It wants to know what are the values of V1. Well, let's see, V1 is going to be here. It wants to know this. It wants to know the voltage at this resistor. Well, in order to know the voltage right here, I'm going to have to know the current right there. What do I know about the current? Because that's what it's going to take for me to do that. It also wants to know V2. Same deal. In order to know the V here, I'm going to have to know the current. And it wants to know R2. It wants to know what this is. So I'm going to need some pieces of information to do this. I'm going to have to do this based off of this right here, because it's the only current that I'm given. What do I know about current in a parallel circuit? Well, first of all, I know this. I know that the current in a parallel circuit is added up. So whatever the current is on this branch, it's not equal over here on this particular side. So somehow I'm going to have to go about finding the current. If I can find the current in this whole piece, then I know the current at every other point throughout the circuit, because in series, it's all the same. So let's see what I could do here. In parallel, we're going to have that the total current is I1, which, well, let's just do it with these numbers. It'll be I3 right here plus I4. Do I have enough information to do this? What I have so far is I have the 0.30 amps right here. But I'm missing this one. I don't know the current through this particular part of it. So this is how I plot my stuff out. I start working through what I need to find. So somehow I need to find I3. Well, in order to find I3, I'm going to need to know the voltage of I3, the current of I3 and the resistance of I3. Well, this is what I'm wanting. I need to solve for this. The resistance is 30 ohms. I don't know the voltage yet. So how am I going to figure out the voltage of this particular part of the circuit? Well, we have some issues, don't we? Let's just keep working. I'm going to have to come back to this in order to get it. I need to find the voltage for this part of the circuit. Well, when I am working in parallel, the voltage of everything is the same. Stuff like this. We don't have 1 and 2 in parallel. We just have 3 and 4. So whatever the voltage is of 3, it also is of 4. But I don't have the ability to, I'd take that back. I do have the ability to find this out. I can figure out the voltage of 4 because I have both pieces. I have I4, I have R4. I have both of those right here. So, aha, we have something. We have 0.30 times 20. 0.30 times 20 is 6. This only has one sig fig, so we're good just taking it forward as this. So what I now know is that if the voltage of 4 is 6, then the voltage of 3 is also 6 volts. Now, we haven't answered a single question yet that we set out to get. Isn't that sad? So now I can solve for I3. I3 is going to be 6 divided by 30, which is 0.2 amps. All right. Still haven't answered a single question, but I'm getting pieces of information now that I need to put over here in order to do the rest of the problems. I have 0.2 now plus 0.3 because I found that. So my total current for this little parallel portion is 0.5 amps. Took a lot of work to get that, didn't it? And I still haven't answered a single question. But what that's let me do is it has let me figure out what my total current is going to be for this. So I'm going to take a different color. I'll take this blue color. What I now know is that the current through this little piece is 0.5. You know what that's helped me do? That's helped me figure out my current for the whole darn circuit. The total current for this circuit is going to be 0.5 amps. And that's what we were missing in order to do some of the problems over here. I needed the I. Well, the current of this is going to be 0.5. So I have enough pieces of information now to work this right here. I need V, I have R, and I have I. So V, I want to know my R is 18 ohms and my I is 0.5 amps. So half of 18 is going to be 9 volts. This right here for V1, 9 volts. That's what this is. 9 volts. Okay. Now, I can do the same exact thing now for, let's see what else I'm missing. I know the I for this one. No, we know the I, right? We still don't know the resistance. So that's what we're looking for, this one. In order to find the missing resistance here, I'm going to have to know the total resistance of the circuit, and I don't know that. So I have a couple different ways that I can go about finding either my total resistance, or I can go about finding the total voltage, or my missing voltage. I can do one or the other. It really doesn't matter. I have to find both of them either way. So in order to find R2, let's just do that next. I know that working in series, my R's are going to be added together. The REQ is going to be the R of this red thing plus my R1 right here plus this missing R. Well, what do I have? I know the red thing is 12. I know R1 is 18, and we want to solve for R2. In order to do that, I need the total resistance, but I don't have it. So how I'm going to have to do that is by working yet another problem. We're going to work a V total problem. I total and R total. My total voltage, I do know. It's 60 volts. My total current, we decided way back here, this was I total for the whole thing, is going to be 0.5. So I can find my total resistance. My total resistance of this whole thing is going to have to be 60 divided by 1/2. So my total is going to be 120 ohms. That goes right here. So once we do 120 minus 12 and 18, we end up with 90 ohms. That one resistor is a huge resistor compared to the others. So our R, where's my cursor? Right here. My R2, that does answer one of our questions, is 90 ohms. So now I've got V1, I've got R2, I'm only missing V2. We need to find the voltage here. Well, we just figured out that R2 was 90 ohms, so now I'm set to do one final problem where I've got V is equal to IR. The voltage at that one is what I'm solving for. The I is 1/2 an amp, and the R is 90. Well, 1/2 of 90 is 45. Now, as far as the sig figs go, you need to knock it up to 50. You'd have to have one sig fig on it. So we would have 50 volts as far as that last one is concerned. That's a lot of steps. This would be like your most possible complicated circuit that you would ever have. And it's so complicated partly because I ask so many questions. I don't think for some of the ones that you get for homework that you have quite so many things to do. I don't ask a ton of these. So you've seen your circuits. You've had series, parallel, and then complicated, complex. You can let me know if you need help